Hello, everyone. Welcome to section 3.2, part 2. We're going to keep talking about polynomial functions and their graphs. So last time we covered some basic tools about how to try to start constructing the graph of a polynomial. We talked about roots, we talked about end behavior, and today we're going to mainly focus on multiplicity of roots. So multiplicity of roots. Okay, so first, let's remember what a root was. So a root or a zero of, oops, can't spell it today, polynomial function let's call it p of x, is a value c such that p of c equals 0. So in other words, it's an x-intercept. It's where the graph of the polynomial crosses the x-axis. It's where it reaches 0. Okay. So now, sorry, if we have a polynomial, and let's say we've completely factored it. So let's say we have a polynomial function p of x in completely factored form. So what that would look like is we've got p of x, and then we're going to get a bunch of linear terms, right? So let's say we've got x minus c1, right? X minus c2, all the way down to x minus cn, right? Now, each of these terms, they could appear more than once. So what we do is we write powers above them, like so. So the x minus c1, that term is appearing m1 times, and then m2 here, and then we're going to put an m instead of n there. Note that all the c1 through cn's, all those are zeros of px, right? Because if you plug c1 into this first term here is going to be c1 minus c1, which is 0. And then it's going to be 0 times, who cares, whatever the rest is. But it's going to equal 0. So c1 is a root, c2 is a root, dot, 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 all the way down to cn. All those are roots of p of x. Maybe to kind of visualize this a bit better, let's see maybe an example real quick. So if we look at like p of x equals something simple like x minus 2, x plus 3, then we have a 0 at x equals 2 and x equals negative 3, right? Standard stuff using the zero product property. We've been doing it this entire time. So the power of the x minus ci term, which up here would be m sub I, is the multiplicity of the 0 c sub I. So to see that up here, c sub 1 has multiplicity m1, and c2 has multiplicity m2, all the way down to cn has multiplicity mn. All right. Again, maybe so we can kind of see this in concrete detail, let's do like p of x, x minus 2, x plus 1. Let's make that one cubed, and let's put an x squared out here. So right away, since it's already in factored form, we know that this first x minus 2, that's going to give us a 0 of x equals 2. So x equals 2 is a 0. And the multiplicity, which I'll just abbreviate as multiplicity 1, because secretly there's a hidden 1 up here, right? And then if we look at the second term, the x plus 1 to the third, that's going to give us a x equals negative 1, which is a 0. And it has multiplicity. Just look at the power, multiplicity 3. Okay, and this last one over here, this x squared, that's going to give us x equals 0 is a 0. And it has multiplicity 2 because it is raised to the second power. So this last kind of just the x right there to some power might be a little confusing, but just remember, if you just see an x sitting outside all the parentheses by itself, you can secretly say that there is like, you can secretly say that this is x minus 0, like that, if that makes you feel a little more comfortable looking at it. All right, so why do we care about the multiplicity of roots? They actually help us graph the polynomial function by telling us what the shape of the graph will be around the root. So here is our rule. And so let's say if c is a 0 of some polynomial function p of x, and it has multiplicity m, m, then we know things about the shape of the graph depending on how m behaves. So if m is odd and it's strictly bigger than 1, these rules only hold for m being bigger than 1. If m is equal to 1, it just cuts right through it usually. We've got two cases depending on the overall shape of the polynomial function. So let's say c is here, and so the graph is going to go through c, and it's either going to look like this, or it's going to just flip and look like this. So it kind of comes in and swoop, and then swoops down, and then kind of just skims over it, and then crosses through, and then goes back down again. Okay. And if m is even and m is greater than 1, then our graphs look more like this. Wow, these are some really bad graphs. Let me try again. C. Okay, so it's going to be one of these two. It's either going to look like this, so it's going to come down and it's going to just touch the axis at C, or it's going to come from below and it's just going to touch the axis at C. Okay, so what this is saying is that if you have a root of odd multiplicity, it's actually going to go through the axis, so it's going to pop out on the other side. But if it has even multiplicity, sorry, I don't know what's wrong with me today. If it has even multiplicity, then it's just going to like kind of glance off of it, but it's still going to be 0. It's just not going to pop out onto the other side. And so what we can do is now we can sketch a graph of the polynomial function. So sketch a graph of, and let's do p of x equals, let's do x on the outside, then times x plus 1 squared, x minus 2. So here we already have something in factored form. To use our end behavior and our, or just to really just use the end behavior, we're going to need to expand this out. So If you FOIL it out and do all the expansions, everything, I think what you get is you get like an x to the fourth minus 3x squared minus 2x. So now we can do what we did in the previous video, and we can look at the end behavior. And so we've got even degree, and then the a, the leading coefficient, is secretly hiding here. It's secretly a 1. A is equal to 1, and that's positive. So when we have even degree polynomial and the first coefficient is positive, then we know that the end behavior looks like this. So as x goes to infinity, p of x also goes to infinity. And just x goes off to negative infinity, p of x still goes to infinity. Okay. There's our end behavior, and we'll use that in a minute. But first, let's look at our roots. Our zeros are at, if we look back up here, so the first one is an x equals 0. And then the second one written, we've got, so x plus 1, which means that 0 is going to be x equals negative 1. And then lastly, we've got x minus 2, so the 0 is going to be x equals 2. And then if you look at the powers up there, the x is all just by itself. It has multiplicity 1. So that's multiplicity 1. The minus 1 is a squared power here, so it's going to get multiplicity 2. And lastly, this one has a secretly 1 hiding there, so it's going to be multiplicity 1 again. All right. So now, with this kind of information, we can actually graph. So let's do that. Okay, so now the end behavior says that while x is very, very, it's way off to the left. So I'm looking at this rule right here. So as x goes off to the left, p of x is positive. So that means that when we graph, we're going to start up here. So if as x went to negative infinity, p of x went to negative infinity, we start down here. But since we are doing this case, we're going to start up here where it's positive. And actually, it'll help if we graph the zeros. So let's make them a different color. So we have at x equals 0, at x equals negative 1, and at x equals 2. And so what we're going to do is we're going to come down. We're going to come over here to the 0. And now we have to decide, are we going to cross the x-axis or are we just going to bounce off of it? So this is where we look at our multiplicity. So we're at x equals negative 1. And it has multiplicity 2, which is even. So that means that it's going to come down here and it's just going to bounce. That's a bouncing root. Okay. So bounce up. And then the next one is right after that, x equals 0. It has multiplicity 1. So we're going to cross right through it. And then for x equals 2, we're going to, again, has multiplicity 1. So we're going to cross right through it again. And here we can indeed see that the end behavior is what we want it to be, right? As x goes to positive infinity, it's still going off to infinity as well. So this is good. So this is a sketched graph. Now, if you're ever unsure or you're stuck, if you're stuck or unsure what the graph should look like based off of the kind of data that you compiled, you can use test points. And so what test points are, they're just points that you pick to plug into the function to make sure that your graph kind of matches up. So the best test points are between the zeros. And to either side of them. So what I mean by that is if we go back up and look at the graph, the zeros here are the green circles, and the best test points are going to be in between them and to either side. So between -1 and 0, -1/2 is good. And between 0 and 2, 1's as good as any number. And then we also want to pick something like on the very left-hand side. So this would be what? -2. And we also want to pick something up over here, which would be 3. Okay, so those are our 4 test points. And so let's make a little list here. So overall, our roots, I'm going to put them in here. I'll put them actually here in green so we keep our colors straight. So this green are our roots. X equals 2. And then the things that we're interested in, the test points we picked are x equals -2, x equals -1/2, x equals 1, and x equals 3. And so now we're going to look at the p of -2. So we're going to plug in our test point into the function. And what we're going to get out for -2, I bet it's going to be 8. And then for p of -1, -1 is just a root, so it's going to be 0. P of -1/2, you plug that in, you do some algebra. I think what you can get out is 5/16. P of 0, again, a root is just going to be 0. P of 1, you plug that in, it's going to pop out a 4. P of 2, again, is 0, so 0. And then P of 3, you plug it in, and it's going to be 48. Okay, so this is a lot of numbers. Oh, sorry, this is a -4. My bad. So these are a lot of numbers, but and how are they useful? So if we scroll back up to our graph and we look at -2, so P of -2, what happens? We plug in -2, we get +8. So here, that does not line up with 8, but that's okay because when we're doing test points, all we care about is whether they are positive or negative. So this one's good. And then we already did the 0. It's already graphed there. And then x equals -1/2, we get positive number, 5/16. Let's see, we plug in 1/2. Yes, indeed, our graph is above the x-axis. That is good as well. And then we've also got next test point is x equals 1. We get p of 1 is -4. And so when we go to 1, we, good, below the x-axis. That's where we want it to be. Excellent. And then lastly, x equals 3. Plug in 3, we get 48, a positive number. So when we're here, yes, it is above the x-axis. That is good. Okay, so that all checks out. So you can use test points to kind of determine like which direction your polynomial is flipped in, et cetera, or you can just use the other kind of data points. You've got options. You've got options to graph these things. Okay. So that was test points and the multiplicity of roots. All this kind of comes together, and now you can start sketching graphs of polynomials, which is very good. So keep practicing that skill, and if you have any questions, I hope to see you in office hours.